Okay, so this is a progress check 12A correction that the teachers have changed the answer to on WebAssign, and I'm about to explain why. I've also modified the mock exam to correspond to these corrections, and this is actually the correction that I was discussing in the exam review. So let's look at this problem. Our problem reads, what is the approximate concentration of free zinc 2 plus when 2.11 e to the negative 2 moles of zinc nitrate is added to 1500 milliliters of solution, that is 0.135 molar hydroxide? For the ion, and they give us the complex ion, the zinc 4 hydroxide 2 minus, then they give us a Kf value. So these problems really don't change a whole lot. We still set up the problems in a similar fashion. We'll write out our our KD, and I'll explain again why in just a moment. We're asked to solve for the free zinc concentration, but this is what our dissociation looks like. We have the complex ion dissociating into zinc 2 plus and 4 hydroxide ions. So let's figure out how much of our complex ion we initially form. We're told that we have 2.11 e to the negative 2 moles of zinc nitrate, and we know anything with a nitrate is completely soluble. So our zinc nitrate produces zinc 2 plus and 2 nitrate ions. Now this zinc 2 plus, since the Kf value is so large, all of this zinc that dissociates will move to form the complex ion. So let's figure out how much free zinc, or how much zinc we have in the solution that moves towards the complex ion. If we have 2.11 e to the negative 2 moles of the zinc nitrate, and we have 1.5 liters of solution, our concentration of the zinc, understand that the zinc is in a 1-to-1 ratio with the nitrate, is equal to 0.0141 molar. And we said that all this zinc moves to form the complex ion because the Kf value is so large. So this is not anything new. We're going to make the assumption that this concentration of the complex ion is 0.0141 molar, and again that came from the zinc nitrate. But this zinc concentration has initially been decreased to 0 because all of it went to form the complex ion. This is where our change occurs with the hydroxide. What we originally had was 0.135 molar hydroxide ion. Well, the 0.135 is no longer 0.135 because some hydroxide was required to form this complex ion. Let's get more specific. We have 0.135 molar hydroxide initially, and how much was required to form the complex ion? Well, that is 4 hydroxides for every 1 complex ion formed. And how much of the complex ion was formed? 0.0141. So once again, this concentration, the original concentration, must be subtracted by this amount to compensate for the hydroxide required to form this complex ion. So this amount of hydroxide initially is now 0.0786. This is the change that the teachers want you to see. We'll be subtracting from x, we'll be adding x over here, and we'll be adding 4x over here. So at equilibrium, our expression should look like this. And if we're going to put it in the expression, we'll say that this is working with the KD, and I said I would explain why we're working with the dissociation rather than the formation. We work with the dissociation because we can ignore X. So the KD value that we're setting this equal to is equal to 1 over KF. So that value is 2.174 e to the negative 18th. So this is equal to X, the products, raised to their stoichiometric coefficients, divided by reactants. And since this value is so small, these x's can be ignored. And when we solve for this value of X, or the free zinc that has dissociated from this reaction, we should find that X's value, what I'm calculating is 8.03 e to the negative 16th. So this value right here is close enough to the WebAssign accepted value. This is only an 8% difference in between these two numbers. So this indeed would be calculated as correct for terms of WebAssign. So again, the major change to understand here is that we have to adjust our concentration of hydroxide to correspond to the amount required to form the complex ion in the first place. So this was from Progress Check 12A. 12B also shows a similar problem, and the 12B work, which this problem reads, determine the concentration of each species at equilibrium when 5.97 grams of cadmium nitrate is mixed with 1,250 milliliters of 0.135 molar sodium cyanide solution, and then they give us a KF for the complex ion. Well, I don't think the teachers have properly corrected this problem yet. However, the work to properly correct this problem we'll talk through. I have corrected it here in front of us, and I'll just walk through this problem, but the WebAssign has not yet been updated to reflect the correct answers that correspond to Progress Check 12A. So let's talk about this real quick. The first step was just like with the first problem that we were just talking about. The cadmium nitrate that is soluble dissociates, and we have to figure out how much of that cadmium can go to form the complex ion. So I take my grams and I convert it into moles, and I find out that I have a 1-to-1 stoichiometric ratio of the cadmium nitrate to the cadmium ion. I then divide it by the volume to establish a concentration. So then I assume that all of this cadmium that has dissociated from the nitrate goes to form the cadmium complex ion here, since the KF value is so large. With this in mind, let's now turn towards our ice chart. We said that this cadmium had decreased to 0 because all of it went to form the complex ion. But here again is the change that I want y'all to see. This concentration of the cyanide is not the 0.135 molar sodium cyanide that we initially had. It's the concentration minus 4 equivalents times the cadmium that was consumed in the formation of the complex ion. So our concentration of the cyanide that has dissociated or remains after we form the complex ion is the 0.135 minus 4 times 0.020. And once again, it's 4 times this amount because we need 4 cyanide for every 1 cadmium that we form here. So this concentration is multiplied by 4. From there, it's the exact same setup. We just have the ice chart that we set up, and we set it equal to a KD, and we solve for X, and we find that the X, which corresponds to the concentration of cadmium, is equal to this amount down here. The cyanide has decreased, and the complex ion is unaffected because the value of X in this equation is so small that it is ignored. So nothing's changed except for the initial concentration, and once again, this has not been properly reflected or updated by WebAssign, but I bet you that your teachers will update it because this is the correct methodology to approach these problems by decreasing the amount of reactant required to form the complex ion here. So that's all that there is as far as the corrections. Once again, the mock exams have been updated to reflect these changes, so take a look at the mock exams on our website.